Hi, today we will see how to use a LiDAR scanner like this to build a 3D map using the Mola framework. Then we will see how to edit the map and finally how to localize into a previously built map. So let me start explaining the different parts of this tutorial. So if you know some of them, you can skip directly to the chapter you need. So first we will see how to install the different software packages. Then we will see how to launch the ROS driver for your LiDAR. In this case, I will assume an Auster LiDAR. And then we will see how to record the dataset. And finally, the two most important parts, building the map and using in localization only mode. For installing the software and for the rest of the parts of this tutorial, by the way, you can check the website of the documentation for the Mola project. I will leave the link in the description of this video. And there you can check the commands and copy them from there. So for installing, I will assume you already have a ROS installation in your system. And then you need to install at minimum all the Mola LiDARometry and Mola packages, which can be done just by using sudo apt install commands as explained here in this installation page, or build from sources if you prefer. Normally, for normal users, it's recommended to install directly from apt. The first step for LiDAR mapping is getting the data out of the LiDAR scanner, convert it into ROS topics. For that, we need two things. First, the electrical connection. Obviously, we need to turn on the LiDAR to plug it into the power and connect the interface into the computer. Normally, they come with an Ethernet connector. So we need to plug the network cable to the computer, whether it is in the robot or a laptop or your desktop. So I will assume that everything is already set up. You have the wiring done. And then, of course, we need the software. We need what is called the ROS driver. It's not a driver in the sense of an operating system, but it's just a ROS package which reads the data from the network and publishes that to a ROS topic. So the installation of the LiDAR driver depends on the manufacturer. I will assume that we are using, as an example, an Auster LiDAR. So this LiDAR comes with a package called Auster LiDAR, which is here on GitHub. So I will assume that you have already installed that. If not, I have left the instructions here on the documentation page on the tutorial. So you can copy that later and build. So you need to clone basically this package and build as usual using colcon build. So once that is compiled, you can enable your local environment as usual using the install setup dot the name of your bash or your shell. And now just to check that we have the package installed, let's try, for example, with ROS2 launch Auster underscore and whatever. So if you click tab twice, you will have the auto completion. For example, Auster ROS. And inside Auster ROS, you have several launch files in XML file format. You can check the Auster documentation for the use cases for them. You have recording, replaying, and so on, driver. But for this tutorial, I will use the sensor one, the sensor launch. Why? Because it's the easiest one for getting the point cloud topics directly published without anything else. The other are useful, for example, if you want to record the LiDAR data and the IMU data into a ROSBAH very efficiently without compressing or without decompressing, let's say, the network package which come from the Ethernet cable directly in the manufacturer format. So if you want directly the point cloud, visible point cloud, you need to use the sensor launcher. So for that, I have left to you this command on the web, so you can just copy and paste this, and you can see all the possible ROS launch arguments that you have to customize this driver. There are many of them, so I am proposing this start point for you. It depends on the use case, but the minimum I would say is something like this. You should launch the sensor launch XML file with these two arguments. The first one is mandatory always, which is the IP address, the network address of the sensor in the Ethernet connection. This may be an IP address or a .local DNS name. I will come to this in a moment. And the second one, the second argument that I recommend is the timestamp mode, because by default the timestamp of the packages of the topics of the messages, the point cloud messages, is the internal oscillator of the sensor, which is fine in many cases, but when you look at the data, at the timestamps, it may seem that you are in the 70s of the last century, which may make the system a bit weird if you have other sensors publishing with a today's date. So it's not the most accurate way of timestamping, but if you use this one, it would use the real clock timer of the computer for timestamping. For more accurate method, you need synchronization with GPS data and so on, but this one is a really good starting point. So the part that is missing now is the network address of the sensor on the network, on the local network, local IP network. So how to find it out? We need to first to configure the network of the computer or the laptop so it sees the sensor. Because right now in your robot or in your computer you have the internet adapter, the network adapter configured to use internet by accessing some cable internet connection or Wi-Fi or whatever. Here we don't want that. We want just to talk to this sensor which is in a point-to-point connection. So that's a different kind of IP configuration. So let's create a different connection profile for this sensor. So for that, go into the network configuration of Ubuntu. It should look like this or similar depending on your Ubuntu version. And then you should have here whatever your default internet connection, and let's create a new one, a new wired connection. It's wired because it's connected through the Ethernet cable. So create a new one, and here in identity I recommend writing something which is human readable and understandable. It's like a local connection for Oster LiDAR. Okay, like that. And then the only thing you need to click here is the IP protocol configuration to click on link local only. We could use manual IP addresses for the computer and then find out the one for the LiDAR, but it's more work, and if you don't have all these concepts really clear, just leave this and it will work. Okay, so link local only connection. It is created. Now you have to enable that. From this moment on, you don't have internet connection. If that was the only Ethernet, the only network interface in your computer, if you have many, you still would have internet connection. But now you can talk with the LiDAR. Okay. Now, what is the address of the LiDAR? So it may have an IP address, but Oster have created this convenient way to access the sensor through a local name, which is like a DNS, but a local one. So The sensors are named after OS, dash, and then the serial number, which is printed here on a sticker somewhere in your sensor. So I will use ping just to check the connection with the sensor. I will ping OS dash and the name of mine. You should use yours, of course. And then dot local. It should work. Okay, here we go. Perfect. So if you see answers from ping, it means that the network is configured right, the sensor is up, you have access to it. Great. You can actually also access the sensor like this directly from your browser, internet browser, and you can check the configuration and such. Okay. So in any way, just doing a ping or accessing through the embedded web server that it has, you can check that the sensor is up, that the address is this one, okay? And now finally, let's launch then the ROS node. So we have the data. So copy and paste this command, and of course remember to replace here your sensor name, okay? And that should be all. So this is the driver starting. It is starting to send commands to the LiDAR, and it also opens up an AirVis window here. So it takes a few seconds to start, if you have noticed that, but now I have the data here. You have on the top a visualization of the range image in a panoramic view, which is as represented as an image, and then on the bottom the 3D points. You can see actually two scans, the 3D one and a 2D one. The 2D one is here, is one on the bottom. Here, laser scan is like a fake 2D scan that the driver publishes just for convenience of legacy method that use 2D method, but we will not use that. So you can even disable here. This is just for visualization, but we don't want it. So if you want to check, this is important, I want you to check that we have the right fields inside each point in the point cloud. Because for accurate motion compensation in LiDAR inertial odometry, we need each point to have X, Y, and Z, intensity, blah, 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 but also the timestamp, the relative timestamp of the point inside the cloud. By default, it is published, but just to check, you can check that here in the topic of the point cloud, which, by the way, is by default /auster/points, is of type point cloud 2, and then you have the channel name here, which is the field, the channel. You should have a T, right? So just double check that you have the T here. Instead of RViz, you can also use Foxglove, which I actually recommend a lot. So you can use Foxglove by first installing the Foxglove bridge if you don't have already, and then launching the Foxglove bridge node, which takes all the ROS2 world into a WebSocket, so the actual Foxglove graphical interface can access it. Open Foxglove, open connection to the default WebSocket, and you should see the data straight away. So you have the 3D view here with the different topics. You can check basically the IMU, the TF static, and of course the points. So for the points, just double check again here that you have intensity and that you have the T for the timestamp. Okay? Okay, and that's all for now. So you have the data coming out of your driver. You can check that also with this topic list. So we are ready for grabbing the data and doing the mapping. So next, we want to record the actual data set for building the map. So once you have your LiDAR running and the data is being published into ROS, There are two ways. We can build LiDAR odometry using a live sensor, running live, or running offline. I normally prefer to run offline because you have more control to tune parameters, to check everything. So that's the way I will focus this tutorial. If you want instead to use the live sensor, the live sensor mapping, you can check the live ROS2 node documentation. That's a different approach with some parts slightly different. So if we want to use the offline mapping, so just take your sensor in your hand, in your backpack, in your robot, whatever it is, and we need to record the data. So it's just a standard ROS2 bug record command. At minimum, you must record the Oster IMU, Oster points, and the TF static. So you have all the different transformations that I formerly showed to you about the sensor inside. So just launch the record, and when you are happy with your dataset, just finish that, and that will be the input to the next stages. So finally, we have the data set, we have everything installed, so we have built the actual map using LiDAR inertial odometry. So I have prepared this long command here for you to directly process any Oster LiDAR dataset. So let's just give it a try for this example that we have recorded here. And later I will explain one by one the different parameters and the different options you have, so you actually understand the different possibilities of this framework. So this is not, by the way, a ROS2 launch, runs independently of ROS2 and can read the dataset from different sources. One of them is a ROS2 bug, like this, like an MCAP file here. Okay, so you can see it started. It has an independent GUI, and I will start later to show to you the different parts here. So for now, we will give to you with a video of the mapping session. So let me go back to this command here, and we will launch that again just to show to you the different parts of the graphical interface of the MOLA inertial odometry system. So in this window, you can see on a small sub window here the raw LiDAR input, so just for verification that the data is coming in. On the bottom you have messages, which are basically a replay of what is printed to the terminal. And on the top you have the sliding bar for the time of the dataset. So on the 3D view, on the main view, you have different switches here to customize the visualization, like showing or not the trajectory. You can see the 3D frame of the vehicle. This is actually the LiDAR because we don't have a vehicle in this example. And the map itself, there are two ways of visualizing. You have the dense decaying clouds, which is like a sliding window of the last n clouds, motion compensated, and with a full density of the LiDAR, we are not something here, I think, just the raw scans, the raw points. The coloring of that is by default using the intensity channel. And you also have the local map, which is the actual map, which is being used for localization and mapping live here. It's not as dense as the other, so by default, that's why by default I am using this one, because it's like more interesting to watch and it has all the details. This local map doesn't mean that the information is lost. As I will explain in a second, you can recover this map later if you want for the full mapping session. So in the control tab of this GUI, you can start and resume the mapping. You can enable the generation of the simple maps, but we have done that already with the command line, so we don't need to do that. And in the status, you can see that everything is running right, like you have the correct rate for the LiDAR and from the IMU and so on. Some parameters important here to watch are the ICP quality, which should be like 90–80% minimum normally. This threshold is a dynamic threshold for the matching between the incoming scans and the map. Is dynamic, which means that when the ICP is having a harder time to match, it goes up. When everything looks perfect, it goes down. You have a minimum and a maximum for that threshold. Is not exactly, but you can think of that like the minimum distance between the point to point for matching, and the number of iterations for each ICP. So the smaller the threshold and the iteration, it means that everything looks smoother and finer. The higher the quality, also the better, right? So once you are happy with this, we can quit the program. We can check, by the way, here on the bottom that the local map has this number of keyframes and the simple map has this number of keyframes. So what is a keyframe? A keyframe is when you store one of the LiDAR scans into a map, into a data structure. You have two independent things here in Mola. You have the local map, which is this guy over here. Well, now it's not shown because the session has ended, but it's the one that was like a low density map. That map is built using this number of keyframes. There is a parameter for how dense how much density do you want into the map, and then how much density do you want for the simple map. This is the map. The simple map is the keyframes that you are saving for later post-processing, and it's the one that will be saved into this file. We have written this from the terminal instead of this GUI, and when I click here, quit, can you see the message? It is saving the final map with 158 keyframes to the map, my map, simple map. Okay. So I have already told the program to do that with these three arguments here. So Mola generates simple map. By default, it's false. If you want to save the map, you need to specify this to true. This is the name of the output file for the map. And this is one of the parameters to customize the density, the distance between keyframes. So this is in meters, 0.2 meters. Every 0.2 meters I want to save a LiDAR scan. This can be 1 meter or whatever you want. The smaller, the higher density of points you will have, the more details into the map, but also the heavier the point cloud will be, of course. So let me explain the rest of the commands here. This is the initial localization method. By default, everything starts and the sensor starts at 000 with the axis aligned with the origin. This instead is a method for averaging the IMU accelerometer, and it infers the orientation, the initial orientation of the LiDAR from the gravity. So it's useful if your sensor is not starting at level. So first, this is really important. So this is the DSQ or motion compensation method. By default, Mola is using a linear interpolation of velocities between one scan and the other. Why? Because in that way it's compatible with any LiDAR odometry, with any LiDAR, without an IMU. If you have an IMU, you need to specify this to use the accurate motion compensation, right? And of course, you need to specify the names of the topics, of the gross topics, like the Auster/IMU and Auster/points, right? And if you remember from the former part of the video, we saw the TF frames. Normally, the base link TF would be called just base link or robot/base link if you are using namespaces. But here I am just using OS sensor because we don't have a robot. So we only have this TF and the TF for the other two sensors. Okay, so we have already went through all the different parameters. I hope that you now understand what have we called here. If you want to get deeper into all these parameters, by the way, you can check on the web. If you go to, not tutorial, but to 3D LiDAR inertial odometry and pipelines, here you have the different pipelines, like this is the default one, generalized ACP, which is actually a YAML file. You can go to the YAML file and look for all the different parameters, or go through this documentation part here when you have the most important ones. But they are even more parameters into the YAML. So if you want to get really into the details, go to the YAML file and study that. Good. So we have our simple map, which is the keyframes map, incorporating the information about the position of the robot and the raw scans. And from that, we can build 3D maps, or a grid map, or a voxel map, or whatever. So that's the flexibility that we have in this Mola framework. This is explained here, by the way, if you go to inertial odometry. So the actual inertial odometry itself takes the raw sensor data and produces a trajectory and the simple map. And then later, we can use these simple maps to build the metric maps using a different program. Okay, so this program is the SM2MM. The name comes from simple map to metric map. We can also first check. So you have my map, simple map here. We can use many programs you have many programs to manipulate all these simple maps, by the way. For example, so if I want to use SM-CLI, okay, you have different options here. We can just, for example, see the information stored into this simple map. And you can see the duration in time, how many observations do you have. Just verify that you have point clouds in it, actually 158 clouds. Okay, we don't have any GPS or something like that because in this example we didn't have that, but we support that also. So the next step would be to create the map, the metric map from the simple map. For that we need to use the SM2MM, and there are different parameters which are required. So obviously the input and the input simple map and the name of the output. But most importantly, the pipeline to use. So SM2MM, the input will be my map, the output will be, let's say, my map again, .mm. But now I need to specify what to do with the raw data to convert into a metric map. For that, I need to specify a YAML file. So, what YAML file to use? I will I will use one of the examples that I have into the MP2P ICP project. If that's not working today, okay, demo effect. So let's copy that from a local copy here. So if you clone the MP2P ICP project, or you also have links into the tutorial page, you can take any of these demos YAML files. There are many of them, depending on whether you want to use like apply a strong voxelization of the data, or just keep a highest possible density, applying different filters, build a voxel map, point clouds only, and so on. For this example, I need to use this guy, which is already here as an example. This one is called SN2MM, no decimation, so just keep all the points. Using IMU motion compensation, applying MLS filtering, and using this type of metric map for the input. Okay, so I will just copy that here. Okay, so it is building the map and applying the final filtering. It will take 1 minute to finish because this filter is quite heavy. Okay, and finally we have the map. I will explain the pipelines later, okay, but for now I want you just to check the results. So let's use mmBOR mymap mm, and this program shows to you the map with the different layers. We only have one layer here, which is called local map, and here we have the final cloud, which is filtered to be like quite flat and noiseless. So here I think it's a quite nice looking cloud for the room. So if you are happy with the cloud, with the map, we can close that. And now let me explain what goes into this pipeline here. Okay, so let me just go into that. So what is an SN2MM pipeline? This takes as input the set, remember, of keyframes from mapping. A keyframe is the pose of the robot together with the raw observations and some context. The context includes information like the motion, the velocities, so things that are useful for applying the motion compensation later. We have 3 parts: generators, filters, and final filters. This is the structure of a generic SN2MM pipeline. Generator. The generator first takes each raw observation and process them. So you can check the documentation for these classes on the MM2P ICP project. But basically you have the default generator, which is called like generator, like this, with no parameters. This is just a name, just for knowing that this is the default one. And this guy is the one in charge of taking the point cloud observations and creating a first layer into the map, which is called raw. Why I am talking about layers, by the way? So in the Mola framework, metric maps belongs to this library, MP2P ICP, and the basic structure is this one, is this class, metric map type. A metric map is not any particular map, but it's just a container with layers. So a metric map like this actually contains a few things. First is just lines and planes, which are quite general, but the most common case is this, layers. It's a vector of layer, not a vector, a map, a dictionary indexed by strings, so it can be any name. You may have different layers, and each layer is an implementation of a map using an MRPT abstract metric map class. When you may have point clouds, different point clouds with different meanings. You may have an occupancy grid in another one, a voxel, a 3D voxel, a bonsai voxel map, any map that you create your own. So it's like are really powerful and generic containers. So that's why I am talking about layers here. So the output of this one will be a raw layer. Now, next, I have this special generator here in this example, which creates a new layer, which is called local map, which is the one that the lidar odometry algorithm expects later for localization. So the localization, when we run that later, expects an input map with this particular layer only. We may have other layers, and it will just ignore them. Okay. So, and this local map layer must have of a specific class. That's why we have the metric map definition here. So just go to the documentation. It's basically a C++ class factory creating any class which is registered into the MRPT registry. You may use plugins, like in this case. In this case, this lidar odometry framework expects a keyframe point cloud map type, which is implemented into this module, and then you have options and parameters for that. So this map will, this layer will not process any observation actually. So it will not be populated with the input raw observations. It will just be created and left alone here, because we will use that later. Okay, so you will have two generators. The first one will process all the point clouds and will generate a raw layer, and this one will create just the local map. Okay, good. So now filters. This filter section will apply in a loop for all the keyframes. Okay, so we start. Remember, we are creating a raw layer here. So the first filter will be a timestamp adjusting filter. I like to use this because different LiDAR manufacturers use different conventions for the timestamping. Some use the zero relative timestamp. I'm talking not about the topic timestamp, but in the inside the point cloud, you have a per point timestamp. Each point has a relative timestamp channel or field. That is typically 0 for the reference timestamp of the cloud of the topic, and then you have a positive or negative small offset, which may be 0.1 second maximum normally, because it's the period of the stamp. This filter here adjusts the timestamp such as the middle is 0. You can use either the first point is 0 or the first one is minus 0.05, the middle one is 0, and the final one is plus 0.05 seconds. So this is what is doing this filter. This must be done before motion compensation, of course, which is the skew. The skew is taking the information from the IMU and generating a new layer, which is called dskewed, using the motion information, the IMU, the local velocity of that comes from the lidar odometry and so on, and generates a new layer with the motion compensated cloud, which is called dskewed. Okay. Next, we can apply different filters here, but in this case, I am just doing a filter by range. So basically, I am removing points in this range between 0 and 3 meters using an L infinity norm, because it is faster than L2 norm. And so this is basically to remove the person carrying the LiDAR, right? Because I don't want the person or the vehicle, the robot, to be mapped as a shadow following the sensor, right? The output will be called the layer called filtered. So we have raw, skew, filter layers so far. And at the end of each keyframe, I want to delete the layers raw and skewed. Otherwise, data will keep accumulating there. Notice that I have not removed or deleted filter. So in the filtered layer, we will have an accumulation of points from all the different keyframes. And this will be the final result in a pipeline, unless you add something else here. So if you, this final step is optional. If you don't add that, you will have a point cloud, you will have a point map in the layer name filtered, and that will be perfect. But it will be perfect for any application if you want to just to visualize the point cloud, for example, or use for anything else. But if you want to use for LiDAR inertial odometry, that algorithm is expecting a map called a layer called local map of the specific type that I mentioned here. So that's why we have the final stage here, and also for filtering. So we take the final layer, which is called filtered, and apply an intensity normalization, okay? And then a noise filter, this is one of the most powerful methods. It's a moving least square filter. It takes the point clouds and basically like smooth the surfaces. There are many different parameters here. You can just check the documentation. And finally, this is important. This is one of the most important filters for the localization steps later. It takes the output from the filter MLS and merge that into the local map layer, which so far was empty until this point. So it's only at the end of the pipeline when you take the filtered points and insert them into the local map object. And then I delete the rest of the layers. We can do something if you want, just to visualize this, how this works. I will just skip this delete stage here, and then I will repeat the processing of the map. It will take a second just because of the filtering, basically, otherwise it's just a couple of seconds. So what is the result here? The result now is the same than before, but with more layers. So if we visualize the map now, you can see here on the Maps tab that you have the filter, local map, and MLS layers. So I can just start disable stuff here, and let me enable, for example, the filtered one, which I can recolor like this by phi or by intensity, which I think that something was wrong, but okay, I will have to check later. But basically, you have the different fields, like the normal directions, and components, and such, okay? And finally, we are into the localization only mode. So, for this case, I will use the ROS actual live node instead of the offline standalone application. So we will use the ROS2 launch for Mola LiDARometry package and the ROS2 LiDARometry launch file. It has many options and different parameters you can check on the online documentation here on ROS2 documentation, and there you can check all the different flags and the meaning. But basically, for localization only mode, we want different things. We want mapping to be disabled, so the map will not be updated unless we later enable that. So at the beginning, mapping is disabled, and it will be also like inactive for localization, because we don't want localization to work until we have a roughly approximated good starting point. We also have this rep 105 protocol disable. So this is the ROS standard way to publish TF using the odometry, map, and base link. We are not following this because we don't have a base link and odometry and odometry, because we are just using one single sensor in this example. And then the name of the topics for the points, for the IMU, the alternative name for the base link frame, as I explained before. In this example with only the sensor, the base link will be the OS sensor frame. And important to enable the IMU based motion compensation for the best accuracy. And then for localization also you need to specify the file that we created in the last step, if you remember. Okay, so let's just copy this. It will be just a standard command for using an Oyster sensor. Okay, so and we can see two GUI windows. We have the MOLA graphical interface here and an RVIF, which already shows the map because the MOLA has loaded the map, has published into ROS, and we are visualizing that here. Okay, that's the path of the data. So you can see in the graphical interface for the control panel for MOLA, you can see that there is no activity, there is no ICP quality because it's not running, because in the control tab is disabled, active is false. Also, we don't have topic incoming, we don't have data from ROS incoming right now. So next, if we are in a real road, with a real sensor, we can launch the Oyster driver node now. Okay, instead of that, what I will do for this example today is just to launch an MCAP that I recorded formerly, but it will be exactly the same than launching the sensor live. Now you can see the LiDAR here on this window. It's not visible on AirViz because we don't have the TF right now because localization is not solved. Let me explain that. I will stop the backplay and show the display section. Okay, you can see the warning here in AirViz. This is normal, this warning here. The map frame is not, does not exist. Okay, the map is not, frame does not exist because LiDAR odometry is not yet initialized and is sending localization data. So it's correct. So this error is expected right now. So what I will do is to let the data to flow a little bit until I reach a known position in the map. Let me check this a little bit. Okay, it's rotating like that. Okay, so I will stop this here. Okay, right now I know where the sensor is in the room. It's something like this. The room is like this, and the sensor is on the bottom. So I will just use the standard topic for this. Comes from the Alt ROS 1 times. This button here is the 2D pose estimate. It's the same one that you could use for a particle filter algorithm. So just click anywhere here. Obviously, it's a 2D estimation. The phi will be grown, the tilt and the roll will be grown, but nonetheless, MOLA will handle that. At the beginning, in the first steps, it will have a hard time to match the LiDAR with the map, but then once it converges, it will get easier. Okay. So right now, we have already clicked here for initialization, but you can see nothing. Well, you can see the message here, relocalize near this pose. So this means that the topic has reached MOLA and it is waiting now to the incoming data and also to be enabled, like active here. So to make it active, you can run this service from the terminal or from another Python interface or whatever, or you can just click here on active. Okay, so both are okay. Right now it should start localizing as soon as I click here resume debug. Okay, so it's localized now, you can see.